The topic of this film is the molecular weight of non-volatile solutes and the method for determining same. We found previously that we can determine the molecular weight of a gas by determining the weight of 22 4/10 liters of that gas at standard conditions. But this method is impractical for substances which don't form vapors at any reasonable temperatures or which decompose upon heating. For these materials, however, a way out is provided by means of Raoult's law, which states that the vapor pressure of a solution is lowered, and therefore its freezing point is correspondingly lowered, by an amount which is directly proportional to the molal concentration of the non-volatile solute in that solution, or that is to the molality of the solution. Now, molality of a solution is, of course, defined as the number of moles of solute per 1,000 grams of solvent. And the amount at the freezing point of the solution is below the freezing point of the pure solvent of that solution in a 1 molal solution is known as the molal freezing point depression. Our first job will be to calibrate the thermometer that we're going to use in carrying out this experiment. This thermometer is graduated from minus 10 degrees centigrade to plus 40, and each degree is divided into fifths so that we can read the temperature recorded by this thermometer rather accurately. In this test tube, I've placed some distilled water, and in this beaker we have a mixture of ice and salt and water. We're going to determine the freezing point of pure distilled water on this thermometer. We know this freezing point ought to be 0 degrees, but it's possible the thermometer calibrations might be slightly in error, and we need to know what the actual freezing point is as measured by this thermometer. To do this, we'll lower the test tube containing the thermometer and the distilled water into the ice-salt mixture and stir until the water in the test tube freezes. We've now been stirring the tube and its contents for a few minutes. Considerable ice is formed in the tube. We'll raise the tube from the beaker. I think you can see the ice crystals inside the tube, but some water still remains. We'll read the freezing point of water as recorded by the thermometer. This turns out to be 1/10 of a degree centigrade. Therefore, we'll record the figure 1/10 of a degree as a starting point in this experiment, because we're going to be concerned with how much the freezing point of water is lowered by the presence of the solute. We've placed a clean, dry test tube on the left-hand pan of the balance and have determined its weight. The weight of the empty tube is found to be 39.657 grams. We'll now place an approximately 4-gram sample of urea into the weighed test tube and then reweigh in order to obtain the exact weight of the sample of urea taken. The tube containing the sample of urea has now been reweighed and found this time to weigh 43.885 grams. This means that the sample of urea taken weighs 4.228 grams. To the sample of urea in the test tube, we will now add 25 milliliters of distilled water using this pipette. We've filled the pipette with water to the mark. It's a 25 milliliter pipette. By removing the finger, we can cause the water to flow into the test tube and onto the urea. We'll rinse down the side of the tube with the water in order to dissolve any fragments of urea that might be on the side of the tube. We will then place the thermometer in the tube containing the urea and stir until urea has all dissolved in the water. And while the final traces of urea are dissolving, we'll lower the tube into the beaker of ice water and determine the freezing point of this solution of urea and water. After several minutes of stirring, the solution in the tube has begun to freeze. I think you can plainly see the crystals of frozen pure solvent, in this case ice, and the fact that there is plenty of solution left. The temperature at this point will be the freezing point of this solution. And reading it from the thermometer, we find it to be minus 4.4 degrees. We know then that the amount of urea that we added to 25 milliliters of water depressed the freezing point so that it now reads minus 4.4 on this thermometer. The data which we've collected in this experiment is now on the board. The observed freezing point of our solution was minus 4.4 degrees. The observed freezing point of water was 0.1 degrees, and this means that the freezing point of our solution was lowered 4.5 degrees. The weight of our tube containing the urea, 43.885 grams. The weight of the empty tube, 39.657 grams, meaning that the weight of urea present in this experiment was 4.228 grams. And the weight of the water in which this urea was dissolved was 25 grams, because we used 25 milliliters of water, and the density of water is approximately 1. From this data, we will now proceed to calculate the molecular weight of urea. We know that the molal freezing point depression for water is 1.86 degrees. Now, the molality of this solution can be easily calculated then, because our solution had a freezing point depression of 4.5 degrees. And if a 1 molal solution depresses the freezing point 1.86 degrees, by dividing 4.5 by 1.86, we see that our solution is 2.4 molal. Now let's let X equal the weight of urea dissolved in 1,000 grams of water. We know then that 4.228 grams were dissolved in 25 grams of water, so we can calculate how many grams will be dissolved in 1,000 grams of water. Well, this comes out to be 169 grams. So 169 grams of urea dissolved in 1,000 grams of water then gives us a solution which is 2.4 molal. And our problem is to find out how much urea it would take to form a solution which is 1 molal. So we need to divide 69 by the 2.4. And this gives us 70, which then is the approximate molecular weight of urea. Now actually, urea has a molecular weight of 60. So we have an error here of 10 parts in 60, or about 17%.